Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today we'll show CFD fluid flow through a Venturimeter using ANSYS Fluent. So we'll start from here, fluid flow Fluent, and we have to import the geometry from here. Let us browse this to select the geometry from the desktop. This is saved in Parasolid format. The model was made using SolidWorks. Next one, we will model this object using ANSYS SpaceClaim. You can see this is the model, but we know that for computation of fluid dynamics, we need to have a closed geometry. We can go for volume extraction. That means inside this Venturimeter, we need to provide closed volume, and we can select the edges required. Extreme right hand side edge is needed, selected, and we have to select the left hand side. Both the edges selected, except this one with green check. Now closed volume will be generated. It is already generated, closed volume, right? If we hide this part, solid part, that means the boundary will be eliminated. Now this is the complete fluid volume. Again, you can check it. This is the fluid volume, and if we accept this boundary, this will be the solid particles. So both can be seen from here. We have to exclude this solid volume, suppress for physics. Let us close this and we'll go back to the fluid environment. Let us update this one. This is the model. You can see boundary is not available. Boundary is actually hidden. We can check it from here again. You can see the geometry and you can see that volume is generated only. The boundary solid parameter is not provided here, right? That is hidden. Next one, we have to provide naming to different cross sections. Let us provide a naming section for this one as exit. Okay, done. Now to select that left portion, that will be named as entry location. Create a named selection for this left hand side as entry. Then select the boundaries and provide the name as walls. With control from keyboard, you can select all the surfaces of the boundary and provide a naming section as wall. It is selected, and we will provide this as named section as wall. Next to that, we have to select the fluid domain, complete fluid domain. So we can select it from here. The whole body is selected, and we can name this one as fluid domain. Okay, done. Next part, we have to provide meshing. Let us select mesh, insert sizing, and it is not selected. We have to select this one. Let us select the whole fluid domain and apply. Next to that, we have to provide sizing of this mesh. Let us provide element size to be 0.005, and we want to provide the mesh behavior to be hard. That means we don't want any kind of software interference. So we want to create the mesh behavior to be hard. Done. Let us generate the mesh. It appears to be fine. Let us update this mesh and we go for next step. Status is showing that mesh translation is complete. Next, we will move on to setup. We want to start the setup with double precision and 3D selection. Let us check different things, like initially we'll check the units. Here in this case, temperature is not an important criteria. Anyway, we'll select temperature to be in Celsius. And you can see the geometry also. So while checking this geometry, it should be seen that minimum volume should not be negative, right? Okay, let us check the meshing quality also. It is showing that minimum orthogonal quality is 3.3 into 10 to the power minus 1. It is okay, because if we see the orthogonal quality, it should be lying between 0 to 1. 1 is good and 0 is bad. Here the minimum orthogonal quality is 3.33 into 10 to the power minus 1. It is okay, right? Okay, next one, we'll go back to models and energy should be on. It will be viscous and laminar flow. Next one, we have to provide materials, fluid, and that fluid can be obtained from Fluent database. We want the default fluid to be water. Copy, close. We have selected the default fluid as water liquid. Solid particles are not needed because we are considering only fluid particles. Cell zone conditions, that means we want to provide that fluid domains should be filled up with water only. Let us provide cell zone conditions as water. So fluid domain is made up of water. Apply this one, close it. Next one, we have to provide boundary conditions, and here in this case we need to have only two boundary conditions, that is entry and exit. Entry, we have to provide water with a specific velocity or a specific mass flow rate. Let us edit this one. Entry, we have to provide water at a inlet velocity of 0.05 meter per second. It will be velocity inlet. Let us edit this velocity. It will be 0.05 meter per second. And thermal conditions we don't want because it will not be that much very important. It will be default as 26.85 degrees centigrade. Apply and close. Next boundary condition will be exit. At exit location it will be atmospheric pressure. You can select this one as pressure outlet and it will be equal to atmospheric pressure. Apply this one, close. Next one, that wall, we can see it will be definitely a stationary wall. Let us see. And we don't want any kind of external interference to this wall, so we'll edit this one as non-moving or stationary wall, and temperature will keep as the normal temperature. It is stationary wall and temperature will be definitely as 26.85 degrees centigrade normal temperature. Okay, let us apply and close. So all the boundary conditions have been applied properly. Next to that, we have to start that methods, and we want to start with simple method and all the others should be default. Next one, we have to see the monitors, and from monitors we're going to keep the residuals within the range of 10 to the minus 6. Okay, done. Next one, we have to start initialization, and it will be a standard initialization, and computation will be started from all zones. Let us initialize. Finally, we have to run this calculation, and we want to have 200 numbers of iterations, and let us calculate. Iterations have already started. You can see it will take some time for completing all these iterations. Let us wait for some time for getting all these results. Okay, you can see calculation is complete. Now we'll see our results. We can see your results from here, and you can see reports. Reports can be seen in different formats. Let us see reports from volume integrals, all fluid domains, and you can see pressure and velocity distribution. Let us select velocity, and when to have volume average, let us compute. Weighted volume average is 0.0768 meter per second. Similarly, we can have different things like pressure also, static pressure. Let us compute. Static pressure is minus 0.72 Pascal. Because at the throat location of this Venturimeter, we have provided minimum cross-sectional area. So at that location, velocity is very high, so definitely pressure will be very less, right? It is in the range of minus 0.72 Pascal. Okay, you can have a lot of other parameters also, like you can see temperature also. Let us see temperature. It will not be changing that much. Let us see compute temperature. It is not having that much of change in this case. Okay, next one we'll see these results from surface integrals. Again, you can see these results. We can see facet average, and we're going to see results from different entities like entry and exit also. We'll select both entry and exit. Let us compute velocity at entry and exit. Let us compute. Average facet velocity is equal to 0.05 meter per second. You can see here at entry velocity is 0.05 meter per second, and at the exit velocity is 0.061 meter per second here at this window, right? So we can see a lot of other parameters also. If we see velocity at the wall, definitely it will be 0. Okay, right? Excluding that thing, we can see other things like pressure at entry and exit. Let's compute. Entry pressure is 5.2 Pascal, and exit it is minus 0.019 Pascal, and the average pressure is equal to 2.61 Pascal. Okay, like this way you can have different parameters. Let us see other things like temperature. It will not be having that much of changes. Let us compute temperature at entry and exit. Entry temperature is 26 and exit also 26.857. So temperature is not changing at all. Now for better analysis results, we'll move on to the next step and see results in a better way. Okay, let's edit results. We can see results in different formats. Initially we'll see results in the form of contour plots, and it is named as contour 1. All domains selected, and we want to see our results from walls. This is in isometric view. Let us see from XY plane only, right? Initially we'll see velocity distribution, and let us apply. So we have already seen this one. Velocity distribution to the walls it is showing is constant. It is 0 at the boundary, right? Okay, let us see pressure distribution again. Instead of velocity, we'll see now pressure distribution. It is showing different ranges of pressure at different levels. You can see as the entry pressure is very high, it is in the range of 5.4 Pascal, and as it is approaching towards the throat of this venturimeter, pressure is very less. At the throat it is minimum pressure, it is minus 1.99 10 to the power 1 Pascal. As in the throat location, area is less, so velocity will be very high. Accordingly, pressure will be very less. When at the exit location, you can see it is in the range of 2.1 to 3.6 Pascal. Okay. At different locations, you can have different types of velocities and pressure distribution. Okay. Right. Next one, we're going to see velocity and pressure distribution in the form of vectors. So what we have to do is we have to hide this previous data, that is contour plot. We have to hide it. Let us deselect this one and we have to select this distribution in the form of vector named as vector 1, and we'll select through walls. Let us see the velocity distribution. Let us select through all faces, walls, exit and entry, all we are considering. Let's apply. This is our velocity distribution in the form of vectors, right? You can see this. So it is clearly understood that at the throat location where the cross section is minimum, in that case velocity is very high, and accordingly definitely pressure will be definitely less. In this throat location, velocity is in the range of 2.12 into 10 to the power minus 1 meter per second, and at the entry and exit it is almost constant. It is in the range of 0.05 meter per second. Okay, right. Next case, we can see dynamics of flow particles in the form of 3D streamline. For that one, we have to hide this pattern. That means this vector pattern we have to deselect. When we can deselect this wireframe also, it is named as streamline 1, and it will be started from entry location. Okay, and instead of 20 numbers, let us make these numbers more. Let us make these numbers to be 100, and let's see. So some kind of turbulent motion we can see at the exit location. This is velocity distribution in the form of 3D streamlines. Okay, we can view these things in the form of animation also. Let us see this animation from here, and let us make the speed very less. We'll make it slow, and we want to repeat this one for 2 times. You can see these things in the form of balls, or even you can see in the form of 3D fish. And for saving these things, we have different formats available. Let us save this one in the form of HD 1080 pixel, and you can save it to a specific location, right? Okay, so we're going to see these things in the form of 3D fish. We'll select that one and let us play it. It is showing in the form of 3D fish. It is quite evident that at the exit location some kind of turbulence is created, and with better design we can avoid this turbulence, right? You can see velocity and pressure distribution at any specific location, at any specific plane, that can be viewed from location and plane. Let us point as plane number 1 at any specific point on xy plane at a distance of 0.001 millimeter away from this. The plane is created. Now next one, what to see this contour plot at a plane which is at a distance of 0.01 millimeter from z-axis. It will be on the xy plane. Let us see all fluid domain, and we're going to see velocity distribution. We're going to see velocity distribution. Let us apply. It is showing velocity distribution at a specific plane which is 0.01 millimeter away from xy plane. It is moving 0.01 millimeter in the z direction. Okay, now let's see pressure distribution also on that plane. So it is providing almost similar behavior. Okay, this is all about today's analysis through ANSYS Fluent. If you want to learn CFD in a better way, you can see my Udemy courses. The link of this one is provided in the description box. If you like this video, please subscribe and share. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.